Hello my dear friends, I am Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So friends, we are studying your first chapter of ICSE chemistry, periodic properties and variations of properties physical and chemical, and till now we have studied or I have exposed you to the entire periodic table, as well as we have studied the concepts till the variation of valency across the period and down the group. Now we are going to study in this video periodicity, periodic properties, and which periodic properties we are going to study? Atomic size and metallic character. Okay, so without wasting much time, let's start and let's rock. So let's see what is periodicity. Okay, it's simply a phenomena in which the properties of elements reappear at regular intervals. Okay, or we can say that it is a phenomena in which the properties of the elements show gradual variation after a regular intervals. Okay, now what does this mean actually? Let's understand this by taking an example. Okay, so here I am taking the example of group 17 elements. Okay, fluorine, chlorine, bromine, iodine. Now here you can see that fluorine has some properties, but after a interval, okay, we will find that the properties which are possessed by the fluorine are reappearing. How? Because they are shown by chlorine, and again after a interval the properties reappear. Okay, how? Because bromine shows those properties, and again after a interval properties reappear because iodine shows these properties. Now I hope this first part is clear to you. Now what does this gradual variation means? Okay, gradual variation means either increase or decrease in the properties of the elements at regular intervals. Okay, now you would understand this thing when we would study the periodic properties in detail. Now just try to understand this in superficial manner. Okay, suppose we are taking an example of atomic size. Okay, so this is the property of an element. Now you would study later that atomic size, okay, when we move from fluorine to chlorine to bromine to iodine, atomic size increases. Okay, so now see, atomic size is the property of element. Okay, it is showing gradual variation, which means either it is increasing or decreasing. Okay, at regular intervals. So when we move from fluorine to chlorine, atomic size increases. When we again move from chlorine to bromine, atomic size again increases. Again in the same case, when we move from bromine to iodine, atomic size again increases. Okay, so now I think the second part is also clear to you. Okay, now we have understood the entire periodicity, means what periodicity means to us. Now what causes this periodicity? Okay, it's very simple. This is because of the reappearance of or recurrence of similar electronic configuration. Okay, now let's understand what does this mean. Okay, we have taken the example of this group 17 elements. So here when I write the electronic configurations of fluorine, chlorine, bromine and iodine, okay, what we find is fluorine's electronic configuration is 2,7, right? Chlorine's is 2,8,7, bromine 2,8,18,7 and iodine is 2,8,18,18 and yes 7. Okay, 53 total. Now you can see here clearly, we already know that the elements in the same group have same number of valence electrons, right? And here they also show the same number of valence electrons. There are 7 valence electrons here. Okay, now because they are having same number of valence electrons, we say that they are having similar electronic configurations. Okay, and because of the reappearance of this similar electronic configuration, okay, we find periodicity. Okay, we observe periodicity. Now is it clear to you? Now let's see why the elements in the same group are having similar physical and chemical properties. Okay, it's very simple. See, the physical and chemical properties, okay, they depend on the number of electrons in the outermost shell. Now we have already studied that in a group okay, all the elements, okay, for suppose I am taking an example of group 17. So in this group, all the elements will have same number of electrons in the outermost shell. Absolutely. Right now we saw there were 7 valence electrons. So if they are having same number of electrons in the outermost shell, and physical and chemical properties are depending on the number of electrons in the outermost shell, so it is very, very clear that they would show similar physical and chemical properties, isn't it? Okay, now let's see what periodic properties means to us. Okay, these are the properties of elements which directly or indirectly depend upon the electronic configurations of the elements, and they also show a regular gradation. Now what does this regular gradation means? Regular gradation means variation, which means increase or decrease, okay, at regular interval, okay, increase or decrease at regular interval. Now how the regular gradation is observed? When we move across the period, which means from left to right, and down the groove, okay, which means from top to bottom, okay, this is left to right. Now you would clearly understand this definition once we start studying about the periodic properties, and I definitely know that till the end you would figure out, oh, what is the definition, what the definition means, okay, of the periodic properties. Now in this entire course we are going to study the 6 periodic properties, which are atomic radius, metallic character, non-metallic character, ionization potential, electron affinity, and electronegativity. Now in this you have to very, very carefully pay attention to this first periodic properties, because rest all periodic properties depend on this periodic property. Okay, now let's begin with atomic size, or we can also call atomic size as atomic radius. Okay, now what actually the atomic radius or atomic size means? Let's see the definition. Okay, it's very, very simple. So if I take an atom, now I know I cannot see it with my own eyes, you cannot see it with your eyes, but if I suppose if this point is an atom, okay, I know it is not having actually the size of a point as well, but suppose, and now I am enlarging this atom for you to understand. So if this is the outermost shell of the atom, okay, and this is the nucleus of the atom, okay, now there is first shell, there is second shell, and this outermost shell, okay, this is our third shell. Now when we see the center of the atom, okay, which is the center of the nucleus, okay, so when we start moving from the center of the nucleus to the outermost orbit, okay, of the atom, the distance we cover, okay, is actually the atomic radius, or we can also call it as a atomic size. Okay, very simple. Now in terms of combined atoms also we can define atomic radius as, suppose we are taking two atoms which are combined, okay, to form a molecule. Now the distance between these two atoms, okay, the distance between the centers, okay, of the nucleus of the two atoms, okay, suppose this is a nucleus, this is a nucleus, so the distance between the centers of the nucleuses of the two atoms, we call this distance as the internuclear distance. Now in this case, when we take the half of this internuclear distance, okay, this is the internuclear distance, we take the half of this internuclear distance, we actually get what? Atomic radius. Okay, very interesting. Now atomic radius, we all know atom size is very small, so it must be measured in units which are actually very, very small, right? So we measure atomic radius in angstrom, and what does this angstrom means? Okay, 1 angstrom means 10 raised to minus 10 meters. Okay, now you try to write 10 zeros, okay, like this, 9 zeros, okay, and then 1, and this much is the 1 angstrom. See, it's very, very small. And similarly, basically we measure the atomic radius in picometers. So 1 picometer is even much more smaller, okay, it is 10 raised to minus 12 meters. So we would add again 2 more zeros and then a 1, and then that would be a 1 picometer. So yes, absolutely, the size of the atom is very, very small, and therefore we use such very, very small units. Now let's see the factors on which atomic size depends. Okay, so first is number of shells. Now when number of shells increases, atomic size increases. How? Let's see. Okay, so suppose I am taking a very tiny nucleus, okay, and this is the first shell, this is the second shell, okay, of our atom. Okay, now you know that the atomic radius is the distance from the center of the nucleus to the outermost shell of the atom. So this is the atomic radius right now. But when I would add again one more shell, okay, I have increased the number of shells, okay, I added one more shell. Now what is the atomic radius? See, this would be the atomic radius, the distance from the center of the nucleus to the outermost shell of the atom. Now you can clearly see that this distance is smaller than this distance. So atomic size increased. Yes. Now let's move ahead to the next factor, nuclear charge. Now what actually this nuclear charge means? Nuclear charge means the positive charge in the nucleus of an atom. Okay, because nucleus has positive charge, right? Now because of which particle the nucleus is having positive charge? Nucleus has two particles, right? Protons and neutrons, but protons are having positive charge. So we can also say that nuclear charge is equals to number of protons in the nucleus. Okay, and you also know that number of protons in the nucleus of an atom is equal to the atomic number of the atom of element, right? So now we correlated nuclear charge to the atomic number because whenever in next discussion, okay, of the periodic properties, if you would observe increase in the atomic number, then you can clearly correlate that yes, nuclear charge is also increasing. Okay, because nuclear charge and atomic number is the same thing now for us. Okay, now let's see what happens when nuclear charge increases. Okay, when nuclear charge increases, atomic size decreases. Oh, yes. Now let's see how. So if this is a very cute tiny nucleus of our atom, this is the first shell, this is the second shell, and this is our outermost shell. Okay, and this is the outermost electron. Now this nucleus, okay, is positively charged. We know electrons are negatively charged, so there would be a force of attraction between the nucleus and electron, right? And this nucleus is attracting electron towards itself. Yes, constantly it is pulling electrons towards itself, right? Now when we increase the nuclear charge, okay, now the nuclear charge increased, okay, nuclear charge increased. So what would happen? Initially the force with which it was pulling the electron, now it would attract more, right? It would pull the electron with more force. Now you only think logically, if the nucleus now is pulling the electron with more force, this would definitely come closer to the nucleus, right? Somewhat here, okay, suppose it's come somewhat here. So now it would start moving around the nucleus here, okay, and this would become the outermost orbit. And now you can see this is the center of the nucleus, this is the outermost shell. So distance between the center and the outermost shell is the atomic radius. Previously what was the atomic radius? Previously this was the atomic radius. Now you can clearly figure out, see, because the nuclear charge increased, the atomic radius decreased. Yes. So now let's see the trends of the atomic size. Okay, how atomic size varies across a period when we move from left to right and down the group when we move from top to bottom. Okay, so first we are going to see the trend of the atomic size down the group when we move from top to the bottom in a group. Okay, now what happens? Atomic size is increasing. Okay, now let's see how it is increasing. So we can figure it out by the help of the factors on which atomic size was depending. So now recall, which were the factors on which atomic size was depending? It was depending on first number of shells, right? And it was also depending on nuclear charge. Okay, now based on these two factors, we could figure out why atomic size is increasing, okay, down the group. Now let's figure it out with the help of an example. So I have taken an example of group 1. Now here you can see that hydrogen is the first member, means hydrogen, okay, of group 1, then lithium, sodium, potassium, rubidium and cesium. Okay, now in this case you could clearly see the number of shells. Hydrogen belongs to first period, that's why we know that the number of shell hydrogen would have would be 1. Similarly, lithium belongs to second period, so lithium would have 2 shells, and the story goes on. Sodium has 3 shells, potassium has 4 shells, rubidium has 5 shells, cesium has 6 shells. Okay, so here you can clearly see that when we are moving down the group, number of shells is increasing. Yes. Okay, so what does this mean? We have studied when the number of shells are increasing, atomic size is increasing. Yes. Now let's see the second factor. Okay, nuclear charge. What is happening with the nuclear charge when we are moving down the group? So what I told is nuclear charge we will correlate it with the atomic number for simplicity, right? So when we would find an increase in the atomic number, we would figure out that yes, the nuclear charge is also increasing. So here in this case, when you see when we are moving from hydrogen to lithium, sodium, potassium, rubidium, cesium in group 1, here the atomic number is also increasing 1, 3, 11, 19, 37, 55. So this means that nuclear charge is also increasing. Okay, fine. Now there is a problem. Now what to do? See, because nuclear charge is increasing, we know that if nuclear charge is increasing, it will pull the electrons closer to itself, right? So atomic size would decrease. Now there came a problem. Now atomic size is also increasing, atomic size is also decreasing. But wait a minute. Yes, we found that the increase in the number of shells, okay, is more than the increase in the nuclear charge. Okay, it is outweighing the increase in the nuclear charge. So this means that suppose number of shells is increasing 2 arrows. Okay, let's understand with this help of arrows. So number of shells is increasing 2 arrows, nuclear charge is only increasing a 1 arrow. Okay, so number of shells here is increasing more than the nuclear charge. So now here if number of shells is increasing 2 arrows, the atomic size would also increase, showing a 2 arrow. Okay, now if nuclear charge is increasing 1 arrow, so atomic size is decreasing, we are showing by this 1 arrow. Okay, correspondingly we are showing the effect. Now what would be the net effect? You could see here the atomic size is increasing because this factor, here the atomic size is decreasing because this factor, okay, because of nuclear charge. Now net would be, see, the increase is more than the decrease, correct? You could just cancel out this increase and decrease, then too the net would remain as the increase, right? And that's why we say that the atomic size increases when we move down the group from top to bottom. Okay, now let's see and just confirm it with the experimental data. Okay, what we found out when we measured actually the atomic sizes of these elements. So hydrogen had atomic size or atomic radius in picometers as 37. Okay, lithium had 152, sodium had 186, potassium 231, rubidium 244, and cesium 262. Now you could definitely figure out, yes, the atomic size is increasing, right? Yes. Now another example is of group 17 elements: fluorine, chlorine, bromine, iodine, astatine. Here also you can see the nuclear charge is increasing consistently, 9, 17, 35, 53, 85, and number of shells are also increasing. So fluorine belongs to second period, therefore number of shells in fluorine is 2. Similarly, chlorine belongs to third period, so number of shells in chlorine is 3, and so on. Bromine has 4 shells, iodine has 5 shells, astatine has 6 shells. So number of shells is also increasing, nuclear charge is also increasing, but we studied that the twist in the story, increase in the number of shell is observed to be more than the increase in the nuclear charge. Therefore, the net effect would be because of the increase in the number of shells, and which is increase in the atomic size. So net effect is increase in the atomic size. You can see here 64, 99, 114, 133, and 140 picometers. Okay, so from experimental data in case of group 17, it is also very clear. So now let's see how atomic size varies across a period when we move from left to the right of a period. Okay, so atomic size decreases. Oh, now let's understand how atomic size is decreasing based on the factors on which atomic size depends. Okay, so we know that the first factor on which it depends means the first factor is number of shells and the second factor is nuclear charge. Okay, now by taking an example of period number 2 elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, let's see how we can figure out, how we can understand the atomic size is decreasing. So here in this case, see, since they are belonging to the period number 2, all these elements have 2 shells, very clear. So the number of shells is remaining exactly the same when we are moving across the period, right, from left to right. What would be its effect on the atomic size? Nothing, right? Atomic size would also remain same, okay, according to this factor. Now, next factor is nuclear charge. So you can here clearly see the atomic number is increasing when we are moving from left to right in a period. So from lithium to neon, when we move, we are seeing the atomic size is increasing from 3 to 4, 5, 6, 7, 8, 9, 10. So this means that yes, nuclear charge is increasing. Okay. Now, what is the effect of increase in the nuclear charge? It would pull electrons towards itself, right? So the atomic size would decrease. Absolutely. Now, because of this, atomic size is decreasing. And now we know that we see the cumulative effect of both these factors. Now, according to this factor, atomic size is remaining same, but according to this factor, it is decreasing. So, cumulative effect or net effect would be the decrease in the atomic size. Okay. So, now I hope you have understood this thing. Now, let's check this thing with the experimental data as well. So, here you can see the atomic radius in the picometers of period number 2 elements. So, in case of lithium 152, then it is decreasing to beryllium 112, then to boron 88, then carbon 77, again it is decreasing 70 in case of nitrogen, 66 in case of oxygen, 64 in case of fluorine. And yes, just wait a minute, okay, don't think about this right now, that how the atomic radius is increasing so rapidly, okay, after moving, when we are moving from fluorine to neon, because the answer of this question we are going to see in the next slide. Okay, now before that, let's again recheck the same thing with the period number 3 elements. Okay, see, number of shells are 3, atomic number is increasing 11, 12, 13, 14, 15, 16, 17, 18. Okay, in this way, and you can also check the atomic radius. Now we know that when we are moving across the period, atomic radius decreases. So let's check with the experimental data. So here sodium is having 186, magnesium 160, aluminum 143, silicon 117, phosphorus 110, sulfur 104, chlorine 99. So we can see that the atomic radius is constantly decreasing when we are moving from left to right in period number 3 as well. Okay. So now what we observed when we were seeing the variation of atomic size across the period, okay, from when we are moving from left to right in a period, that when after fluorine, okay, the atomic size was found to be increasing, okay, in case of neon. Now the actual trend says is that the atomic size decreases, okay, across the period when we move from left to right. But how then after fluorine the atomic size is increasing in case of this inert gas neon? Okay, now the question would be arising in your mind whether it is happening in the case of this fluorine neon pair, or it just happens in the cases of all the other halogen and inert gas pairs, okay, of the same period. So yes, absolutely right, you are right, it is happening with the chlorine and argon as well. After chlorine, when we move to argon, there is an increase in the atomic radius or atomic size. After bromine, when we move to krypton, there is an increase in the atomic size. And similarly, after iodine, when we move to xenon, there is an increase in the atomic size. Now, we can generalize this in the form of this question, right? That why the atomic size of the inert gas, okay, are greater than, okay, are greater than the halogens. Okay, these are the halogens of the same period. Now, the answer is very, very simple. Now, as we know that these inert gases are having completely filled outermost shells. Okay, now this completely filled outermost shell means their outermost shells are filled to the extent that they are having maximum number of electrons, okay, in their outermost shell. Now, because they are having maximum number of electrons in their outermost shell, the electron repulsion is also maximum, okay. Now, because of these electron repulsions, okay, which are maximum, these electron repulsions are actually outweighing the increase in the nuclear charge. Okay, now what does this mean? These electron repulsions, simply if we simply put this thing, what does it mean? If these electron repulsions, okay, or the repulsive force between these electrons is much more than the attractive force between the nucleus and the electrons. So now you can imagine that they are repelling each other with such a force which is greater than the attractive force between the nucleus and the electrons. So absolutely they would move away from each other, and in this case when they are moving away from each other, okay, what would happen? The outermost shell, okay, or they would move away from each other. In this case they would move away from the nucleus as well, and since they are moving away from the nucleus, the distance between the center of the nucleus and the outermost shell would increase, and yes, that's why we are seeing an increase in the atomic size in case of inert gases. Okay, now you could observe one thing as well. See, the atomic size of inert gases is more than that of the halogens, absolutely, but it is less than that of the alkali metals, okay, or the group 1 elements of the same period. Here you can see neon is having 112 picometers atomic radius, but lithium is having 152 atomic radius. So yes, absolutely it is less than the alkali metals or the group 1 elements of the. Now let's see why the size of the cation is less than the parent atom. Okay, parent atom means the atom from which the cation is formed. Okay, now first let's understand how the cation is formed. Okay, very simple. By taking an example, you would understand this thing. So I'm taking an example of magnesium atom. Okay, means I'm taking a magnesium atom. I would tell magnesium atom, oh magnesium atom, just lose your one electron. So yes, he is losing its electron, or it is losing its electron. Now after losing an electron, what it would become? It would become a positively charged magnesium ion. Okay, now why is this positive charge on this magnesium? Because here in this case there were 12 protons and 12 electrons. Okay, why I'm saying 12 protons and 12 electrons? Because I know magnesium's atomic number is 12. So this means it has 12 protons, and since it is an atom, it has 12 electrons. Okay, but after losing an electron, what would happen? It would still have 12 protons. Okay, but it has lost one electron, so electron number would be 11 here. So since it is having one more extra proton, it is having 1 plus charge. Very simple. Now, so this thing would be cleared. When a cation is formed by the loss of electron, what is happening? Okay, the number of electrons are less than the protons. Number of electrons are less than the protons. Okay, now suppose this is a game of tug of war. Here there are 12 protons and there are 12 electrons in this case. Okay, but now what happened? We lost an electron, means magnesium lost an electron. So here there are still 12 protons, but there one member is reduced, 11 electrons has become. So now this 12 protons would definitely pull this 11 electrons with more force. Yes, and that's the thing which is happening. Okay, here in the case of Mg plus, 12 protons are present in nucleus. So this nucleus is now pulling the electrons, okay, with more force. Okay, it is attracting electron with more force. Now what would happen? If these electrons are attracted with more force, they would come closer. Now if these electrons are from outermost orbit, okay, they are also attracted with more force, so they would come closer, and since they have come closer, the outermost orbit came closer, and outermost orbit came closer. So now the distance from the center of the nucleus to the outermost orbit is now less, right, as compared to the atom. Okay, in case of atom, the distance was this much. Okay, but when it formed an ion, it had 12 protons. Okay, it had the same number of protons, but number of electrons reduced. That's why nucleus started pulling the electrons more strongly. Since it started pulling the electrons more strongly, outermost electrons, okay, the electrons in the outermost shell came closer. So in this way, outermost shell itself came closer, and since outermost shell itself came closer, so now the distance between the nucleus and the outermost shell reduced. So the atomic size is found to be reduced in case of cations. Okay, very clear. Now one more interesting feature: when the charge on the cation is more, okay, or when the charge on the cation, for suppose we are taking an example, okay, this is Mg2 plus ion and this is Mg plus ion. Okay, now here the charge on the cation is plus 1, here the charge on the cation is plus 2. Now when the charge on the cation is more, its size is less. Okay, how? The same logic. See, here in this case there are 12 protons and 11 electrons, but now the Mg plus 1 would again lose an electron to form Mg2+. So this means that out of 11 electrons, one more electron would get reduced. So it would become 10 electrons and 12 protons. And now in this case, okay, the force with which 12 protons are pulling the 10 electrons is, yes, absolutely correct. It is more than this case in which 12 protons are pulling 11 electrons. Now, since these are pulling the 10 electrons more strongly, so the same story repeats. The outermost shell would come closer and the atomic size would be less. Okay, here you can see the atomic size would be. Now, let's move ahead. Let's see why the size of an anion is greater than the parent atom from which it is formed. Okay, parent atom means from which the anion is formed. Okay, now same story we will go on, we will see here. Now in this case we will take an example of fluorine. Now this is the fluorine atom. Now I am telling him that yes, you be an anion right now. So what it would do then? It would accept an electron. So here it becomes a F minus ion. Now why F minus? See, here there are 9 protons and 9 electrons, but in this case, since it has accepted one more electron, so from 9 the number of electrons become 10. So since it is having one more extra electron, it is having one more extra negative charge, one more unit extra negative charge. So this is represented by this minus charge. Okay, minus charge. So F minus ion. Now here you can clearly see the 9 protons are pulling 9 electrons in the game of tug of war, right? But here 9 protons are pulling 10 electrons. Now the same logic we will apply. In this case, the force of attraction, okay, or the force with which nucleus is pulling the electron, it would be more, right, than in this case, because here there are less number of protons, so they would absolutely pull the 10 electrons with less force, right? So since they are pulling with less force, what would happen? Suppose this is a fluorine atom, okay, but after gaining an electron in its outermost shell, now it became a fluoride ion, okay, F minus ion. Now the 9 protons are not pulling the 10 electrons, okay, with that much force as compared to the 9 protons are pulling 9 electrons. So that's it. So they are pulling with less force, means the force of attraction between the nucleus and the electron is less right now. So if this force of attraction is less, then the electron would move slightly away from the nucleus. It would move away from the nucleus, and if it moves away from the nucleus, what would happen? The distance from the center of the nucleus and the outermost shell would increase, and since the distance is increasing, we say that the size of the anion is greater than the size of the parent atom. Okay, very clear. Now let's learn about the size of the isoelectronic ions, but before that, first let's see what actually the isoelectronic ion means, right? Very simple. You can remember it from its name itself. See, iso means same, electronic, so from this here you can derive electrons, so same number of electrons, and here it comes ions which are having same number of electrons are called as isoelectronic ions. Very simple. Okay, now the size of these isoelectronic ions depends on the nuclear charge. How? Since they are having same number of electrons, what is varying in them? Absolutely right, number of protons. So that's why their size depends on the nuclear charge, that is the number of protons. Okay, now how it depends? When the nuclear charge is increasing, their size is, nuclear charge is increasing, see, the size is decreasing. Absolutely, it should. Okay, now let's understand this with the help of example. Okay, here Mg2 plus, Na plus, F minus, O2 minus are isoelectronic ions. Why I am saying they are isoelectronic ions? Because if you would see, they are having same number of electrons. Okay, O2 minus, an oxygen atom has 8 electrons, but 2 minus suggests that it has 2 more negative charges than the protons. Okay, so 2 more negative charges means there are 8 protons, but 2 more means there are 10 electrons then. So here see, you can see 10 electrons. Same with the case of fluorine, 9 electrons, 9 protons, but negative charge suggests that 1 more electron is present, so 10 electrons. Similarly, Na plus, it has 11 electrons and 11 protons, but since it is showing plus 1, which means 1 positive charge is more. Okay, so 11 protons, then if they are, from 11 protons, if one positive charge is more, which means that there should be 10 electrons, right? So here 10 electrons. Mg2 plus, 2 positive charges are more, so 12 protons are there, but there should be now 10 electrons to make 2 positive charges more. So here also see 10 electrons. So now you have understood how these all are isoelectronic ions. Now what is happening? See, O2 minus has 8 protons, right? So its size is 1.42 angstrom. Now when we move to F minus, it has 9 protons. So now you would now imagine the same tug of war game. There are 8 protons here and 10 electrons there. So 8 protons are somehow trying to pull 10 electrons. It's fine, it's okay. So that's why the size is 1.42 angstrom. But now there are 9 protons. Oh, one more member is added here. So now they would start pulling electrons with somewhat more force. Since they are pulling electrons with somewhat more force, the electrons would come closer. Electrons are coming closer. The outermost shell is coming closer. In fact, outermost shell is coming closer, which means the size is decreasing. And here you can see 1.26 angstrom. From 1.42, the size has decreased 1.26. And similarly, the same case goes on. In case of Na plus, there are 11 protons. So, oh, the number of protons is now more here. So now they would feel more energetic, right? They would pull the 10 electrons with great force. Now, again, they are pulling the 10 electrons with a force which is greater than the F minus and O2 minus. So, absolutely the electrons would be very much closer than the case of F2 minus and O2 minus. So, if they are very much closer, the outermost shell is closer. In fact, outermost shell is much more closer than F2 minus and O2 minus. So, this means that the size is smaller in case of Na plus, okay, than in the case of both these ions. So, you can see here 0.95, it is smaller than both these cases, okay, 1.26 and 1.42. And the similar story goes on for the Mg2 plus ion. Its size is, now in the case of this Mg2 plus ion, okay, there are 12 protons. So highest number of protons are found in this isoelectronic ion as compared to other isoelectronic ions, right? So these 12 protons would pull the 10 electrons like anything, and they would bring these 10 electrons closest to themselves as compared to all the other isoelectronic ions. So the outermost shell would be closest, right, to the nucleus as compared to other isoelectronic ions. So this means that the size would be smallest, okay, as compared to other isoelectronic ions. So here you can see the size is smallest, 0.65 angstrom. Okay, so now what we learned from this concept is actually whenever you are given isoelectronic ions, okay, a set of isoelectronic ions, and you are asked to arrange these isoelectronic ions in the increasing or decreasing order of their size, you have to just pay attention to the number of protons in those ions. Okay, more the number of protons, here you can see smaller would be its size because it would pull the electrons like anything, right? And least the number of protons, larger would be its size because it won't pull the electrons with that much force. So electrons won't come closer and the size would be the largest, okay, in comparison to other ions. So we are done with atomic size, our first periodic property. Now let's see our second periodic property, metallic character. Okay, so what does it mean, metallic character? Okay, so it simply means metal like character. Okay, now what character do metals show? We can say that metals show a tendency, okay, to lose the valence electrons to form a cation. Okay, how? Suppose this M is a metal, so it has a tendency to lose its valence electron. Okay, so suppose this is the outermost shell of the metal, this is the valence electron of the metal, so it would lose this electron and form a cation. We all know, okay, this process. Now see this tendency, okay, if an element is showing this tendency, that is to lose the electron and form of cation, then we say that that element has metal like tendency or metal like character. Very simple. Now this means that if this tendency to lose electron, okay, is more, okay, this tendency to lose electron is more, then absolutely the element is showing more metal like character, right? More metallic character. Very simple. Now you have to just understand this thing very clearly and bus by understanding this very thing, it would be very easy for you to understand the trends of metallic character, okay, when we move across the period, when we move down the group. Now, one more interesting question you can observe is, okay, we call hydrogen's cation as proton. Okay, have you observed it? Yes. But why do we call the hydrogen's cation or cation of a hydrogen a proton? Very simple. Okay, see, hydrogen only has one proton in its nucleus, okay, and a very much poor one electron in its first shell, okay, which is the last shell. Now, after losing this electron, hydrogen becomes H plus. Now, see, what is remaining now? Just one proton is remaining, right? That's why we call this cation of hydrogen as proton. Okay, now let's see the factors on which the metallic character of an element depends. Okay, we are going to follow, let me tell you that we are going to follow a particular pattern in which we are going to learn the periodic properties. So, firstly, we are going to see what actually the periodic property means to us. Then we are going to simply see on which factors that particular periodic property depends. And then lastly, the trends of that periodic property. Okay, so we followed this pattern for learning the atomic size. Now we are going to follow this pattern for learning the metallic character as well. So, we just saw what metallic character means to us. Now, let's see on which factors metallic character of an element depends. So, from here onwards, the periodic properties, rest of all the periodic properties would be depending on two factors. First is atomic size and second is nuclear charge. Now, what is our job? What actually we are going to learn? We are going to just see what happens when the atomic size increases and nuclear charge increases to a particular periodic property. Okay, so let's see here what happens when the atomic size increases. To whom? What happens? To the metallic character of the element. Okay, so let's understand this with the help of an example. So, I am taking a very cute atom, okay, whose nucleus is this, and this is its outermost shell. Okay, now the outermost shell is having this electron. Now, what I am going to do is I am going to increase the atomic size. So, if I have increased the atomic size, okay, if I am having another atom, okay, suppose, which is having this much size, okay, so now you can clearly make out the size of this atom, okay, is less and this atom is more. Now, this is the outermost shell of the second atom. Now, this is the electron of the outermost shell, electron present in the outermost shell. Now, what is happening? See, here in this case, nucleus is pulling the electron. There is a nuclear pull on the electron. Now, in this case as well, okay, nucleus is having a pull on the electron. But can you make out? Here the distance between the nucleus and the electron is less. Okay, here the electron is moving farther from the nucleus. So, in this case, the nuclear pull which this electron would experience would be less as compared to this case, right? In this case, the nuclear pull an electron would experience, so it would be, either we can say it would be more than this case. Okay, now try to understand or try to think logically. If the nucleus is pulling this electron more strongly than this electron, so which electron you think would be easy to lose? Okay, this one or this one? Yes, you are right. We can comparatively, it is easy to lose this electron. Okay, so which means that it is easy to lose the electron when the atomic size has increased, okay, as compared to the previous atomic size. Now, if it is easy to lose this electron, then we can say that the tendency to lose the electron, okay, or the ease with which an electron can be lost is more in this case. So, we can say that the tendency to lose the electron is more in this case. Okay, so now if tendency to lose the electron is this much, okay, now we have also learned if the tendency to lose electron is more, then the metallic character is also more. Okay, so this suggests us that the metallic character is also more in the case when we have increased the atomic size. Okay, in the case of an atom which has a more atomic size as compared to the atom which has a lesser atomic size. So, what it suggests here, the tendency to lose electron is suppose this much, okay, as compared to this, and likewise if the tendency to lose electron is this much, the metallic character is also this much. Okay, now you can clearly make out here. See, when we increased the size of when we increased the atomic size, what happened? The metallic character also, boom, increased, right? So very, very simple. When the atomic size increases, metallic character increases. Okay, now let's see what happens to the metallic character of an element when the nuclear charge increases. Okay, again we are going to take a very, very cute nucleus and a very, very cute atom. Okay, this is the outermost shell of the atom, outermost electron of the atom. Now the nuclear charge is, suppose, now we have taken a nucleus which is having, suppose, XYZ nuclear charge. Okay, now having this much nuclear charge. Okay, simply, so it would pull the electrons with some attractive force. Now what we are going to do? We are going to increase the nuclear charge. I'm just showing the size of the nucleus as bigger. It doesn't mean the nucleus becomes big. Okay, I'm just trying to represent it, an increased nuclear charge. Okay, so what would happen? Now the electron would be pulled by the nucleus with more force, right? So now you only think logically. Here, when the nuclear charge has increased, the force of attraction with which a nucleus pulls an electron has increased. Okay, so would it be easy to lose electron now, okay, than the previous case when the nuclear charge was less? Yes, you are right. When the nuclear charge was less, it was easy. It is easy to lose the electron as compared to the other case when the nuclear charge increased. Okay, so now I'm showing this increase with these two arrows. Okay, previously nuclear charge was this much. So the ease, what we just now saw, the ease is more here. Okay, when the nuclear charge was less, the ease to lose the electron was more. Okay, as compared to this case, the ease is less. Now, if the ease is less, if the ease is more, the tendency is more, simply. And if the tendency to lose the electron is more, then we know that metallic character is more. Now, similarly here, if the ease is this much, so tendency would also be this much, and the metallic character would also be this much. So now here you can figure out, when nuclear charge we increased when the nuclear charge, what happened? Initially the metallic character was this much, but now after increasing the nuclear charge, metallic character decreased, right? So this simply, the nuclear charge increases, metallic character decreases. Okay, now it's time to see the trends of the metallic character of an element, right? So first we are going to see, yes, you are right, down the group from top to bottom. When we move from top to bottom in a particular group, what happens to the metallic character? Okay, metallic character increases. Okay, now it would be a question the question would have been arised in your mind, that how we are going to remember so many trends of this metallic character, of this periodic properties, right? The factors on which that particular periodic property depends, and then you have to just think logically what would happen when that particular factor increases, or when that particular factor increases. Okay, just that thing. When you would figure out what would happen when that particular factor would increase or decrease to the periodic property, you would definitely guess out, or you would definitely come to know that what is the trend of the periodic property. Okay, when we move across the period and down the group. Okay, feeling confused? Don't worry, you would get the clear picture right now. Okay, we are going to follow the same thing. Now let's see how an metallic character of an element increases when we move down the group. We are just going to rely on the factors on which metallic character depends, and we are just going to think logically. Okay, see, I'm taking a group 1 elements example. Okay, lithium, sodium, potassium, rubidium, cesium. Okay, we are not going to take francium because francium is radioactive, so we don't know the properties of the francium that much, okay, in detail. So let's not move to the francium, let's not get into the francium, consider up to cesium. Let's consider the group 1 elements up to cesium. Now, what is happening? We know that metallic character depends on two factors, atomic size, nuclear charge. So when we move down the group, yes, we know atomic size increases. We have just now studied, right? Now, atomic size, if it is increasing, so right now what we saw, when the atomic size was increasing, it became easier to lose the electron. So tendency was more to lose the electron, tendency is more, metallic character is more. So metallic character here in this case is increasing, okay, when the atomic size is increasing. From this factor, we we got this we reached here. Okay, now let's see the second factor, nuclear charge. What happens when we move down the group to the nuclear charge? See, the atomic numbers increase, right? Lithium has 3, sodium has 11, potassium 19, and so on. So atomic number increases, which means nuclear charge also increases. Okay, so what happens to the metallic character when nuclear charge increases? Just now we saw, when the nuclear charge increases, it becomes difficult for the electron to lose. Means it becomes difficult for the atom to lose the electron. If it becomes difficult for the atom to lose the electron, then the tendency to lose the electron is becoming less, right? And if the tendency is becoming less, metallic character would decrease, right? So here it is decreasing. Now you would think, oh, metallic character in this case is increasing, metallic character in this case is decreasing. But yes, you have to remember this thing very clearly. Okay, when we are moving down the group, atomic size increases, but the increase in the atomic size is much more than the increase in the nuclear charge. Here you can see. Okay, much more means it is outweighing the increase in the nuclear charge. So suppose atomic size is increasing this much, nuclear charge is increasing only this much, right? It is outweighing the increase in the nuclear charge. So the factor, okay, so this factor is contributing to the increase in the metallic character. So now if it is increasing more, the metallic character is also increasing more in this case. If it is increasing this much, so metallic character would only decrease this much only. Okay, one arrow, that's it. Now what would happen? Since, okay, this factor, okay, increase in this factor, atomic size, is outweighing the increase in the nuclear charge, so the net result, okay, whether the metallic character would increase or decrease would depend on this factor only, right? So here see, if we cut these two arrows, okay, so net would be the what? Increase, because increase is more than the decrease of the metallic character. So yes, we figured out why metallic character is actually increasing. Okay, and we also figured out the trick to remember how the periodic properties vary down the group, right? Now let's see how the periodic properties vary across the period. Okay, now let's see how the metallic character varies when we move across the period. Okay, very simple. We are going to apply the same logic. What we are going to see is how the factors on which metallic character depends varies across a period. Okay, so let's take an example. Second period elements I am writing down: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, now here you can see the atomic number is increasing: 3, 4, 5, 6, 7, 8, 9. 9. Fluorine has 9. So here we can clearly make out that nuclear charge is increasing when we move across the period. Okay. Now we know that when we move across a period, what happens to the atomic size? The first factor, okay, on which metallic character depends. We have just now studied the trend of atomic size across the period, and you can remember this thing in the form of visualization. Okay, so we have just now saw that, okay, few slides ago when we were studying the trend of atomic size, the atomic size of lithium is the largest, okay, in the entire period. Then the atomic size goes on decreasing. Okay, so you can just remember in this way. Okay, just a visual representation of atomic size. So here you can clearly make out, oh, atomic size is decreasing. Okay, so in this way you can remember. Now, what is happening when the atomic size decreases to the metallic character? Okay, now let's see in this case, and then what is happening to the metallic character when nuclear charge increases. We already know when atomic size decreases, okay, the metallic character would be decreasing, right? Because now the electron is moving closer and closer and closer and closer to the nucleus, so it would be difficult for the electron to remove or for the electron to lose for an atom. So if it is becoming difficult for the atom to lose the electron, the tendency to lose electron would be less. Less tendency to lose electron means less metallic character. So in this way we are going to understand. Okay, so less metallic character. Very easy. Now let's see what happens when nuclear charge increases. We already know nucleus will pull the electrons like anything, so it would be difficult for the electron to lose, and if it is difficult for the electron to lose, the tendency to lose electron would, yes, you are right, decrease. Less tendency to lose the electron, less would be the metallic character, so metallic character would also decrease. And now it is very much clear from these two factors that the overall effect is decrease in the metallic character. So see, we reached the trend. Okay, we reached the answer. What happens across the period? Metallic character decreases. So in the second period, lithium would be the most metallic element, right? Because metallic character is decreasing, and fluorine would be the least metallic element. Okay, so similarly we can see when we are seeing the example of third period elements. Okay, so sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. So in this case as well, okay, same pattern is observed. Metallic character is decreasing when we move across the period. So sodium would be most metallic element and chlorine would be the least metallic element. Okay, now let's see what reducing agent means. Okay, very simple. So such elements which lose their electron to complete their octet, okay, are called as reducing agents. Very fine. Now we just now studied which elements lose their electron to complete their octet or to form cation. You're right. Metals have the tendency to lose electron, right? So can we say metals are reducing agent? Yes. So fine. Now one more interesting thing. See, if an element has more tendency to lose electron, okay, more tendency to lose electron, so we can say that that element is a strong reducing agent. Okay, very simple to remember. What you have to just remember is, or what you have to just understand is, tendency to lose the electron. Okay, if an element is showing tendency to lose electron, it is a reducing agent, right? More is a tendency to lose electron, more stronger is the reducing agent. Simple. Okay, so you have to remember this thing very clearly. Why? Because now we will correlate this with the thing which we have learned earlier. Do you remember what we have learned? More is the tendency to lose electron. It also means that the element has more metallic character, right? Are you remembering? So yes, so this means that the metallic character, okay, more would be the metallic character when more is the tendency to lose electron. Stronger would be the reducing agent, or we can say more would be the reducing nature, okay, when more is the tendency to lose electron, okay, shown by an element. So this means, see, the reducing nature and metallic character are depending on the same factor. Okay, so we can say that when the metallic character is more, reducing nature will be more, right? So we have just now studied the variation of metallic character across the period down the group. So let's just go through it. So when we move from left to right, what happens? Metallic character decreases. Okay, and when we move from top to bottom, what happens? Metallic character increases. Now see, more metallic character means more reducing nature. So we can also infer from this that when we move from left to right, reducing nature will decrease. Okay, I am writing this Rn will decrease. Okay, because here the metallic character is more. Okay, so reducing nature would be more. Here the metallic character is less, so reducing nature will be less. Okay, so from more to less we are moving. That's why we are saying metallic character is reducing. Okay, are you understanding this thing? So if here it is more, then the reducing nature here is also more. Here if the metallic character is less, reducing nature is less. So this means reducing nature is also varying from more to less, which means the reducing nature is also decreasing. Similarly, if here metallic character is increasing, reducing nature will also increase. Okay, so I am telling you a trick to remember the trend of reducing nature. What it is? You would have figured out right now. That simple trick is, see, reducing natures, the trend of reducing nature of an element, okay, of the elements when we move from top to bottom or when we move from left to right, okay, in a period and in a group will be similar to that of the trend of metallic character. Okay, so someone if asks you, tell me the trend of reducing nature of the element from left to right, what you have to do? You have to just remember the trend of metallic character and your work is done. So friends, with this we have reached the end of this video, and I hope you all would have enjoyed learning with me and you would have understood all the concepts so far we have learned. But please do let me know whether you have understood all the concepts or not. And yes, we are going to meet in the next video with the remaining concepts of this chapter. And as you all know, LearnoHub matlab free hai par best hai. So see you in the next video. Stay tuned. Bye bye and have a great day.